We all kind of grow up with this idea that our brain is pretty much done by the time we're, say, 18. Like, the major construction is over, and from then on, we're just living in the house. Well, it turns out that couldn't be more wrong. Your brain is a work in progress for way, way longer than you think. And we're about to take a look at just how deep that construction project really goes.
So, let me just ask you straight up. When do you think your brain is actually truly, fully cooked? When does all that development finally settle down? Just take a guess.
Yeah, whatever age you just thought of, it's almost certainly too early. We're talking about a process that goes on well into what we all consider adulthood, and it unfolds in some really fascinating and frankly, kind of surprising ways.
All right, so let's get into our first big idea. For a huge part of your life, your brain is running this massive behind-the-scenes rewiring project.
That's right. From the time you're about 12 all the way to your mid-30s, your brain isn't just chilling out. It is actively giving itself a major hardware upgrade. And this isn't some chaotic mess. It's a very purposeful, highly organized period of intense change.
So how's it doing this upgrade? Well, the main tool it uses is a process called myelination. The easiest way to think about it is this. Your brain's pathways, its neurons, are like tiny electrical wires. Myelination is basically the process of wrapping those wires in a fatty insulation called myelin.
And this slide shows you exactly why that matters. An uninsulated wire, like you see on the left, has a slow, leaky, and pretty unreliable signal. But once you wrap it in that myelin insulation, bam! The signal becomes lightning fast, super focused, and incredibly efficient. This is literally the upgrade that's happening inside your head for decades.
But here's where it gets really interesting. This upgrade doesn't happen everywhere at once. Oh no. Different parts of the brain get rewired at totally different speeds, and for very different reasons. It's a fascinating trade-off.
So a huge study back in 2020 really laid this out for us. It showed that our brain develops two different kinds of circuits. First, you've got your fast circuits. These are in the parts of your brain that control things like movement and your senses. They get a real thick coat of myelin to make them super fast and automatic. Then you have your flexible circuits. These are in the regions that do all the heavy lifting, complex thought, decision-making. They get a much lighter coating of myelin, which actually keeps them more adaptable and open to learning new things for a lot longer.
And this image right here is just a stunning look at that whole process in action. This is what's going on in an adolescent brain. The areas you see in red, that's rapid myelination. Those are the fast, efficient motor pathways coming online. But the areas in blue, that's much slower development. Those are the flexible, cognitive circuits, the parts that handle emotion and big decisions. You're literally looking at a brain that's being built for action first and reflection a bit later.
Now, as we move out of our teens and into our 20s and 30s, that really sharp contrast starts to even out. The frantic, uneven growth begins to slow down, and the entire system becomes much more balanced, much more integrated. And that's what gives us a more stable, mature brain.
But hold on, that is only half the story. It turns out there's another clock ticking away in the brain, a metabolic one. And it seems this clock doesn't tick at the same speed for everyone.
Which, of course, brings up a really big question. Beyond these general patterns we all go through, are there more fundamental differences in how our brains age over a lifetime?
Well, to figure this out, researchers at Washington University tried something totally different. They didn't just look at the brain's structure, they looked at how it uses energy. They got a sophisticated AI, a machine learning algorithm, to analyze brain scans from 205 adults to measure their brain's metabolism, basically how much fuel it's burning.
And after crunching all of that data, the AI came back with one very specific and pretty mind-blowing number: 3.8 years.
So what in the world does that mean? It means that, on average, a woman's brain has the metabolic profile of a brain that is nearly 4 years younger than a man's brain of the exact same age. And this isn't something that just shows up late in life. They could see this difference even in the youngest people they studied who were in their 20s.
Now, it's really important to be clear about what this means because it's a subtle point. The study's lead author, Dr. Mano Goyal, explains it perfectly. He says it's not that men's brains are aging any faster. It's that they seem to enter adulthood with a brain that is already metabolically about 3 years older than a woman's, and that gap just stays consistent for the rest of their lives.
So, okay, let's pull all this together. We've got a brain that develops unevenly until our 30s, making this trade-off between speed and flexibility. And we've got a brain that seems to have a different metabolic clock for men and women. So, why does any of this actually matter?
Well, it really comes down to how the brain uses fuel, and the brain's main fuel is sugar.
See, a metabolically younger brain is one that's still using a lot of that sugar for processes that support growth and maturation. The fact that women's brains appear to stay in this state of metabolic youth throughout their lives might be a huge clue as to why, on average, they tend to experience less cognitive decline as they get older. If there's one big thing to take away from all this, it's that your brain is on a much longer and more complicated journey than we ever gave it credit for. It's a journey with different paths for different abilities, and it runs on these deep biological clocks that seem to tick at different speeds for different people.
It really just makes you wonder, doesn't it? I mean, we've only figured out these incredible, decades-long rewiring projects and these fundamental metabolic differences in the last few years. If this is the kind of stuff we're learning right now, what other incredible secrets about how we think, how we feel, and how we grow is that amazing brain of yours still waiting to reveal?